So we're going to do the worksheets of week 7, and we're going to begin with a review one. So we want to find the derivative of the function cosecant of x ln x. And for that, we need to recall the product rule, the chain rule, and certainly the derivative of cosecant, which is negative cotangent of whatever you have inside, times cosecant of whatever you have inside. So that's the derivative of cosecant times the derivative of the inside function, which according to the product rule is going to be 1 times ln x plus x times 1 over x. There are a few simplifications to be made here, but we're not going to bother with them. Next thing we want to do is find the derivative of cosine to the 10th of x. And it would be best if we thought of this as cosine of x all raised to the 10th power. It's as if you have something raised to the 10th power. And we can use the chain rule, and this will be 10 cosine of that to the cosine of x to the 9th power. So let's write it this way. And we need to multiply by the derivative of what we have inside of cosine, which is negative sine. And then we have a couple of integrals. The first integral is the integral from 0 to pi over 2 of cosine x sine x dx. This integral, we're going to encounter it a little later in the course. It can be done very easily by doing a substitution. U is equal to sine x. Du will be cosine x dx, which means that this integral will turn into u du. And we have to be careful with the endpoints. We have to plug them into sine. So we will have sine of 0, that is 0, and sine of 1, sine of pi over 2, which is 1. So this will be u squared over 2 from 0 to 1, which is 1/2. And we have a last one, which is the arctangent. I remind you that the arctangent is also known as tangent to the -1, depending on what source you're looking at. And this can be done quite easily by just an integration by parts. Think of the function 1 as the derivative of x being in front of arctangent, and apply your integration by parts. So this is x arctangent of x minus, and now you will have the integral of x times the derivative of arctangent, which is 1 over x squared plus 1. If you like to think in terms of u's and v's, then u prime is 1, which means that u is x, and v is arctan of x, which means that v prime is equal to 1 over x squared plus 1. And you have this formula. So now it remains to actually find this integral. This integral can be found quite easily by doing a substitution. U is equal to x squared plus 1. Du will be 2x dx. We don't have a 2, so x dx is the same thing as 1/2 du. So what do we have? We have x arctan x minus 1/2 du over u. And of course, this is x arctan x. The antiderivative of 1 over u is ln of u. Ln of absolute value of u, we don't need the absolute value because we have x squared plus 1. So when we plug it in, we will get minus 1/2 ln of x squared plus 1. If you want, you can put absolute value, but it's redundant because this quantity is positive. And that's this integral. Okay, why don't we go on with this week's problems, which are based on finding the tangent plane to a surface and the linear approximation. I remind you that the tangent plane, I remind you that the surface in this course comes in two varieties. We have the graph of a function of two variables, and we also have a level surface of a function of three variables. So let's start with the first problem that says find an equation for the tangent plane to the graph of the function f of xy is equal to x ln of x plus y at -2, 3, and 3. And here when we say 3, this is really f of -2, 3. We recall that we find the graph by juxtaposing the inputs with the output. So what we need to know here is that the tangent plane is going to look like z is equal to f of -2, 3 plus f sub x at -2, 3 times x minus 3 plus f sub y at -2, 3 times, I'm sorry, here it should have been x plus 2. Sorry about this. Let me erase this. Okay, let's write it nicely, x plus 2. And then we have y minus 3 here. So if you look at this function, this is the linear approximation. It's also the first order Taylor polynomial. It's really the only linear function that shares with f its value at -2, 3 and the first two partial derivatives there. So we need to find these three numbers. Actually, we know this number. This number is 3, as we said. What is f sub x? F sub x will be ln of x plus y plus x over x plus y. And if you plug in -2, 3, you will find simply -2. And f sub y is equal to x times 1 over x plus y plus 1, which means that f sub y of -2, 3 is going to be -2 plus 1, which is -1. So if we put everything together, we will see that our, oops, what happened here? We don't want this, right? Let's go back. Okay, so it's going to be z is equal to 3 minus 2 times x plus 2 plus -1 times y minus 3. And that's the equation, or at least an equation for the tangent plane. Okay. Now, let's go to our second problem. In our second problem, we're going to work with a surface which is given as a level surface of a function of three variables. As you're going to see, no explicit three variable is given, which means that we will have to cook it up. In any case, let's take a look at the statement. It says find an equation for the tangent plane to the surface x squared minus y cubed plus xyz plus z to the fourth is equal to 2 at the point 2, 1, negative 1. Okay, so what do we do here? The first thing we need to do is to define a function that has this surface as a level surface. So we define f of x, y, z. Just bring everything to the left-hand side. It doesn't really matter. You can just, you can put these things, you can leave it like this, or you can put -2. If you leave it without the -2, then it's going to be the level surface corresponding to 2. If you put it like this, then it's the level surface corresponding to 0. So let's write it. So the given surface is the level surface of f of x, y, z corresponding to 0, to the level value 0, if you will. So for this, the gradient at the corresponding point is perpendicular to the surface at that point. Hence, it is normal to the tangent plane. Okay, first of all, what is that gradient? So f sub x here is 2x plus yz. F sub y is minus 3y squared plus xz. And f sub z is xy plus 4z cubed. So we get, oops, sorry. Seems that Zoom sometimes is playing these games. So f sub x of 2, 1, negative 1 is going to be what? 4 minus 1, I guess, which is 3. Right. And then f sub y, it's not my lucky day, is it? Let's see. Okay. And f sub y at 2, 1, negative 1 is going to be how much? Minus 3, minus 2. So that should be negative 5. And f sub z at 2, 1, negative 1 will be what? It will be 2 minus 4, also known as negative 2. So that tells you that the gradient at the point we're interested in is going to be the vector 3, negative 5, negative 2. So what do we have here? We have a plane whose equation we're looking for. We know it goes through the point 2, 1, negative 1. And we know that a normal vector to that plane is given by the gradient that we just found, which is 3, negative 5, negative 2. So we should be able to put its equation together quite easily. 3 times x minus 2 minus 5 times y minus 1 minus 2 times z plus 1 is equal to 0. And notice how this equation differs, its format at least differs from what we have seen, what we saw in the first example. And let's go to the last example, where we're given this function, f of x, y, z. Where do they come up with these functions? Oh, I forgot I came up with these functions. I don't know how to answer this question. So anyhow, here's the function. The idea is to make the denominator nice, right? That's pretty much the main idea here. And we want to find the linear approximation, find the best linear. Sometimes we don't call it the best, we just call it the linear approximation. It's only one. It's the first order Taylor polynomial of this function, pretty much. Even though in our course we don't do Taylor polynomials. Around, meaning centered, at the point 1, 4, 2. Okay, and then once we have found it, we would like to use it in order to estimate f of 0.8, 3.9, and 2.1. Okay, let's see how we do this. So this is a problem of several differentiations. Let's set a goal. So let's write down what the linear approximation is going to be. So the linear approximation is simply f of 1, 4, 2 plus f sub x at 1, 4, 2 times x minus 1 plus f sub y at 1, 4, 2 times y minus 4 plus f sub z at 1, 4, 2 times z minus 2. Okay, so we clearly want to compute these four numbers. That's how we're going to get started. And what is f of 1, 4, 2? So what happens if we plug in 1, 4, 2? We're going to get 4 plus 2 is 6. So this number is 6, right? This number is 6. About the derivatives now. Well, let's take the first derivative with respect to x. Quotient rule. So we will have the derivative of the top is y times x squared plus z squared minus y times the denominator minus xy plus z times 2x, derivative of the denominator with respect to x over x squared plus z squared minus y. We just need to focus on the denominator. So what do we get? Get this nasty thing first of all. So let's get rid of it. And then we want f sub x at 1, 4, 2. Okay, how much is this? So it's going to now be 4. And then what we have is also, so this part here is 4, as I said, and then you have 6 times 2 minus 12. So 4 minus 12 is negative 8, and the denominator is 1. So that's negative 8, right? How much is f sub y? F sub y is going to be, let's apply again the quotient rule. So it's going to be x is the derivative with respect to y of the top times the bottom minus the top times the derivative of the bottom, which is negative 1 over x squared plus z squared minus y all squared. And this will give us that f sub y at 1, 4, 2 is equal, again, let's do our computation. So we will have this whole thing is 1, right? And then you have this thing that is 8. It's not 8, it's 6. Sorry about this. 6 And you have two negatives, so that should give you a 7. And let's finish with f sub z. So we will have what now? We will have 1 times x squared plus z squared minus y minus xy plus z times the derivative of the denominator, which is 2z, over x squared plus z squared minus y squared. So f sub z at 1, 4, 2 is going to be how much? So this whole thing is 1, right? Okay. This thing we said is 6. And then you multiply by this, which is 4. And pretty much you get 1 minus 24, also known as negative 23. So now we can put together the linear approximation. So f of g, I'm sorry, of x, y, z is going to be 6 minus 8 times x minus 1 plus 7 times y minus 4 minus 23 times z minus 2. And so f of x, f of the point we're interested in, which is 0.8, 3.9, and 2.1, is approximately equal to g of 0.8, 3.9, 2.1. Let's see what we're dealing with here. So we have, this will be 6 minus 8, and you have times 0.2. This is 0.2. It's 1 minus 0.8. Plus 7 times what? It's 3.9 times minus 3.9 times minus 4. So that's negative 0.1. And we also have minus 23. And this is 2.1 minus 2, which is 0.1. Okay, let's see what happens with this. So we have 6 minus 1.6 minus 0.7 minus 2.3, right? So if you add all of these things together, what you're subtracting, you find minus 4.6. So it's 6 minus 4.6. Oh, I'm sorry. This first one was, we have two minuses here, right? Sorry, this was negative, so this is plus 1.6. Okay, so we will have 7.6 minus 3, that will give you 4.6. Okay. And I guess that does it. So thanks for watching the video. See you next week.